Now we turn to the what's known as the Watt topographical mapping, qualitative and quantitative mapping of the brain, which is quite original, has never been produced in this form in the literature. And one would agree that it provides a vital part of the essential needs when studying neuropathogenesis, and that is to establish the pattern of the disease in the brain. Before this topographical mapping was done, the diagnostic histopathology was carried out, and that will be referred to later. What one saw on histopathology was the perivascular cuffing, represented by a circle, the cell nodule, represented by the dot, and this is represented by hemorrhage, this asterisk. And so one follows the pattern of the disease throughout the whole of the brain by using transverse coronal sections, whole transverse sections which can fit on a large slide. We will see that there is a pattern of disease in which the lesions are less numerous in the front part of the brain, but more towards the ventral part. All of these lesions were related to the neuroanatomy, and that will be described in the text of the figures. But here I want to show you the actual pattern of the disease, where here we're seeing predominantly perivascular cuffing with associated cell nodules close by. Now, as you can see, the intensity of the lesions is increasing as we go posteriorly towards the midbrain. One can see here, once again, the perivascular cuffing, the cell nodules, and here is a lesion which is called either focal micromalacia, or you could call this lesion a focal microinfarct, and I'll show you the lesion in histopathology later. So these are really infarcts, but they're not caused by embolism. I will show later that they're caused by hypoxia when the virus has destroyed the parent blood capillary endothelial cells. But at this stage, you can see that this focal micromalacia, or what could be called the Watt microinfarct, is closely associated with the perivascular cuffing and the cell nodule, and it's mainly in the ventral part, and it's in the midbrain area, more intense. And look, and you'll see that by and large it's similar on both sides. So when it's similar on both sides, the logical deduction from that is that this particular pathogen arrives there via the bloodstream, and we'll follow that more and more later. So if we go on to the next slide, this figure, one can still see the intensity of the lesions is still strong. There is the microinfarct or micromalacia, focal micromalacia here, and the perivascular cuffing associated with the cell nodule. And once again, it's more towards the midbrain. It's more ventral in the midbrain area, the brain stem area, and less up here in the cerebral hemisphere region. So I am postulating that there's a good reason why these lesions have a predilection for this part of the brain and not the other part, and I'll be referring to that later. Now here in figure 17, about the same density, same quantity of lesions, perhaps a little less than in the previous. Once again, qualitatively, perivascular cuffing, cell nodule, and a bit more distribution, a little bit of some distribution in the cerebral hemisphere, but still mainly confined to this ventral part and the brain of the brain stem. And the hippocampus is obviously affected as well. Here the hippocampus is affected. The changes here are more marked, more severe, in that there's more severe microinfarcts, as I call them, or micromalacia. I call this microinfarct, as I'll refer to later in histopathology, because there's a coagulative necrosis which is related to hypoxia because the blood capillary cells in these cell nodules have been destroyed. So what I will be depicting later, and what I'll find by a combination of light microscope and electron microscope, is that these cell nodules actually represent the presence of the virus within blood capillary cells. And therefore, if you follow the pattern of these dots, you can see the pattern of the distribution of the virus throughout the brain. Once again, you notice that it's rather evenly balanced on both sides, which again tends to provide stronger evidence that this is viremia. It's a blood-borne. And when one goes to the ultrastructure and also to the histopathology, you'll see that it's got a specific fundamental lesion in the cell nodule. This has never been described before. The fact that the cell nodule represents the site of the antigen. Other workers have reported the perivascular cuffing. They've reported the presence of cell nodules, which is characteristic of a virus disease, but they've never looked at why there's perivascular cuffing and what is going on at the blood capillary level. These perivascular cuffs are in small blood vessels, but not blood capillaries. So by logical deduction, one would expect the blood capillaries to be affected as well as the small blood vessels, but they haven't been looked at so far until this publication. So later we will see that here is the micromalacia, which is hypoxia. Infarcts, as you know, are produced by emboli, which block the blood vessels. The evidence here suggests that a similar type of effect is produced, but it's hypoxia associated with multifocal blood capillary endothelial cell necrosis, which produces this coagulative necrosis here and is associated with the virus that's present in that cell nodule, which I'll show later. These here are showing evidence of neuronal degeneration. So you have neuronal changes here in this midbrain, much more severe because of the presence, which is indicated by the presence of this coagulative necrosis, which I'll show you later in histopathology, and associated neuronal degeneration. Now, this will be investigated further to produce new discoveries associated with this neuronal change. That neuronal change is associated with the hypoxia and not, I repeat, NOT, not with primary invasion of the virus into the neuron. Now, the primary invasion of the neuron is the current dogma in both Teschen-Townsend disease in the current literature, and it's also the current dogma for human poliomyelitis. And I will show that, in fact, this neuronal change is produced by hypoxia because the parent blood capillaries are producing hypoxia to these dependent neurons. And this is also reflected in the coagulative necrosis, which is characteristic of a hypoxia, not of a viral invasion. A viral invasion is characterized in this virus by lysis, liquefactive necrosis, not coagulative necrosis or a partial degeneration of the neuron, which they're showing various degrees of degeneration of the neuron, but not lysis. That lysis, the liquefactive lysis, is demonstrated in the parent blood capillary cells within those cell nodules. And we'll demonstrate that in due course with histopathology, then ultrastructural studies. But here it shows a great intensity of the lesions in that area. And later I will attempt to provide scientific evidence for why this is occurring in this particular spot. In other words, nominating the predilection sites and why they're occurring. And one will mention that this appears to be a physicochemical effect of changing the blood flow as opposed to specific chemical receptors, which is the current dogma. With chemical receptors, the flaw in that argument is that the chemical receptors, specific receptors, can be found where the disease is not present. And if that's the case, then the case is flawed. Whereas with this situation, there is a correlation between the capillary necrosis and the associated degeneration of neurons, and also demyelination, which is a characteristic lesion of this disease, which hasn't been given enough attention so far. And the lesions that are occurring in the dorsal and ventral roots, in the dorsal root ganglia, and also in the spinal cord. There is subtle but specific demyelination, which is a characteristic of this disease. Now, when PIG-H recovers, there are various reasons why this pig recovers. And one of the reasons proposed is that there's remyelination of those demyelinated areas to permit that animal to walk normally again. So this has great ramifications in human disease, because one can see that it is possible for an animal model to recover, and it's also possible for a human patient to recover It's of great significance clinically. And there are other reasons why Pig H, Harold, recovered, and I'll go into that later. So we now proceed with the topographical mapping, the qualitative and quantitative topographical mapping, which shows the pattern of the disease, which is absolutely vital when one is studying neuropathogenesis, particularly studying the mysteries of the etiology and general causation. So here we can see that most of the lesions are in this area, and the lesions, these areas are rather devoid, except in the hippocampus here, devoid of lesions. The question is, why is this happening? I'll proceed later, and you'll see that as we proceed quarterly, we're in the vital areas of the brain concerned with basic metabolism, high energy areas, therefore high energy requirements, therefore high energy blood requirements, therefore high needs for oxygen. And so what happens in the body is that there's a variation in the complexities of the blood capillary cells and the networks. There's an increase in the blood capillary networks in vital areas, high energy areas. That's only would seem to be natural that should happen. And in fact, it's been shown that that's the case. And the surface area in these particular areas of the brainstem have a much higher, greater surface blood capillary cells than in other areas. Because of the increase in surface area, this makes them more vulnerable to friction and slows things up. And I'll show you later that the cells, the leukocytes, and even the thrombocytes, the blood cells, develop villi or pseudopodia, and also that occurs in the blood capillary endothelial cells. And so you have these villi with increased surface areas which are added to the high surface area of the blood capillaries. And so there's a general slowing down of the blood and a greater random chance, in my view, a greater random chance for the virus particles to get off their ride that they've had on the leukocytes, which I think they have, and hit the certain blood capillary cells. So here we see the neuronal degeneration associated with the cell nodule, which reveals is present the virus in the blood capillary cells, and there is the perivascular cuffing. Here in slide 20, one sees another lesion, which I've called the microinfarct of Watt. And the reason for calling it that is to draw attention to this new type of lesion and the new concept of its pathogenesis. Later on in the histopathology, we'll see that this is actually coagulation necrosis, and coagulation necrosis is by definition associated with hypoxia, not with virus invasion. So this once again consolidates or reinforces the concept that this disease begins in the blood capillary endothelial cells and not in the neurons or elsewhere. Once again, one can see the close association, a more severe form here, a lot more blood capillaries affected, and perivascular cuffing. Later on, I will talk again about the evolution of what I've called the Watt theory of relative blood capillary circulation pathology, in which this can be defined as the the rate of morbidity and mortality in the dependent cells, that's the neurons and glial cells, nerve fibres and the like, varies directly with the severity of the mortality in the parent cells, that is, the blood capillary endothelial cells that supply them. And so this is an explanation for severity of changes. What I'm proposing here is that there's a greater number of blood capillary endothelial cells showing necrosis, showing death, and that's reflecting in the hypoxia of these areas, much more severe here. And so not only can we, by studying these patterns of diseases, we can conceptualise the severity and explain the severity of the lesions as well as the distribution of them. Now we're moving from the midbrain, where there are quite a large number of lesions, to the medulla oblongata, another vital area, as you well know, and therefore likely to be, and if my theory is correct, then good reasons for finding many lesions, because these are vital areas with a high complexity of blood capillary cells which are needed to provide the energy for basal metabolism. So here we have high numbers with considerable neuronal degeneration in that area, near the cerebellar peduncles, considerable perivascular cuffing, and cell nodules. It must be remembered that when one sees perivascular cuffing, one is not seeing the fundamental lesion, because there's the Virchow-Robin space in there which prevents the virus from moving over into the rest of the neuropil. Whereas with the blood capillary endothelial cell, as you know, it's adjacent. There's only the cytoplasmic membrane for the virus to get in. So that's the reason, it's anatomical. That's the reason why it's more likely that the virus will get into the blood capillary cell rather in the small blood vessels associated with perivascular cuffing. But perivascular cuffing is an indicator, and almost invariably with viruses one sees cell nodules. Unfortunately, research workers in the past have not really looked at that cell nodule. They've just noted that it is a cell nodule or a glial nodule, and they haven't examined it closely enough to reveal the mysteries of Mother Nature. The mysteries of Mother Nature are that that virus is showing a initial lesion in the body, in that cell nodule. And therefore that's a vital part of pathogenesis, neuropathogenesis, because the definition of neuropathogenesis is the initiation, the mechanisms underlying the initiation of this virus in the body and its subsequent spread. That's what, in case of neuropathogenesis, obviously in the nervous system, pathogenesis in general, the same condition, same explanation. Here we have considerable neuronal change, perivascular cuffing, cell nodules, the same here. And roughly speaking, a fair balance between, not so much there in that case. Quite often it depends upon where you actually slice it. It might be just out a little bit in the way that it's actually sliced. But in general, there's a balance between both sides as you go down the brain, which is indicative of a viremia. That was confirmed in my research by the finding of the virus in the blood capillary endothelial cells, and that plus the histopathology, this plus the histopathology led me to go looking in the cell nodule to find what I hoped would be there, and I found it. So here we're in the medulla oblongata, and there's considerable neuronal degeneration and some perivascular cuffing, but it's quite severe in these areas here. This is the cerebellum. One can see that the lesions here are not very high in number. In some other virus diseases and Teshand, severe form, other workers talk about more severe lesions in the cerebellum, but the evidence here does not support that the cerebellum is severely affected. Now we come to the spinal cord. Sections were taken from the more cranial parts, the mid part and the caudal parts of the spinal cords, and lesions were found in all parts right down the spinal cord. The explanation for the clinical signs is somewhat controversial in a sense, because lesions are present. The clinical signs show that it's mainly a posterior paresis or paralysis, but in some cases it may be more severe in the forelegs. But mostly, as you saw in the clinical cases, the animal could take its weight on the forelegs, the front legs, F-O-R-E. And so it's really, again, a matter of severity of those lesions, the number of blood capillaries that are affected. And it's quite possible that the blood capillary network might be greater in the hind legs than in the more towards the front, because of greater energy needs for them. Certainly in man, walking as he does on two legs, one would think that there'd be a higher demand, high energy demand, where the legs are in relation to the muscular nervous supply in hind legs. But at the moment this is in need of further research. So again, one sees the characteristic lesions, perivascular cuffing, the cell nodule, and the neuronal degeneration.